I am Sandra CV. My topic is algorithm analysis. So, first we need to know about what is meant by algorithm analysis. So, algorithm analysis can be defined as an important part of computational complexity theory, which provides a theoretical estimation for the required resources of an algorithm to solve a specific computational problem. That means the analysis of algorithm is the determination of the amount of time and the space resources that is required to execute it, and the analysis of algorithm that generally focus on the CPU time, usage, the memory usage, and disk usage, network usages. And two important terms here we need to know is the performance and complexity. So the performance means how much time, memory, disk, etc. that is used when the the program is run. This depends on the machine, compiler, etc. as well as the code we write. Next is the complexity. Complexity means how do the resource requirements of a program or the algorithm scale. That is what happens as the size of the problem being solved by the code get more larger. Next, why the analysis of algorithm is important, or the importance of algorithm analysis. The first point is to predict the behavior of an algorithm without implementing it on a specific computer. And next is it is much more convenient to have a simple measure for the efficiency of an algorithm than to implement the algorithm and test the efficiency every time a certain parameter in the underlying computer system that changes. And next is it is impossible to predict the exact behavior of an algorithm because there are too many influencing factors. Next is the analysis is this only an approximation. It is not a perfect. It is not always need to be perfect. Next is more importantly, by analyzing different algorithms we can compare them to determine the best one for our purpose. And some other these are some of the important points for that why the important algorithm analysis that become so much important. And there are so many other reasons also available, and some of them are the performance, the performance of the performance prediction. That means it helps to predict the algorithm's behavior and the suitability for large inputs. Next is resource optimization. It guides in optimizing time and memory resources. And next is comparison of algorithms. It provides a basis to compare different algorithms for the same problem. Next is scalability, that ensure that the algorithm can handle larger inputs more efficiently. Next topic is the types of algorithm analysis. The first one is best case. Best case evaluate the minimum time or space of an algorithm that requires for any input of size n. That means the best case can be defined as the input for which algorithm that takes less time or minimum time. So the best case that calculate the lower bound of an algorithm. For an example, in a linear search, when the search data is present at the first location of large data, then best case occur. Next is ROST case. ROST case that evaluate the maximum time or space of an algorithm that requires for any input of size n. So the ROST case defines input for which the algorithm that takes long time or maximum time. That means in ROST case that calculate the upper bound of an algorithm. For an example, in linear search, when the search data is not present at all, then the ROST case occurs. Next is average case. Average case that evaluate the expected time or space of an algorithm that requires on average case considering all possible inputs of size n. That means in average case that take all the random inputs and calculate computation time for all inputs and then divide it by the total number of inputs. That means the average case equal to all random case time divided by total number of cases. In that way we can compute the average case. Next is amortized analysis that evaluate the average time per operation over a sequence of operations and spreading out the cost of expensive operations. For an example, for dynamic array resizing, the amortized time complexity for the insertion is big of 1. Next is probabilistic analysis. It evaluates the expected performance using the probabilistic methods, taking into account the distribution of inputs. For an example, in randomized quicksort, the probabilistic analysis can show that the expected time complexity is big of n log n. Next is there are some examples for this types of algorithms. First one is insertion sort, where the Rost case is big of n square when the array is in the reverse order, and average case is big of n square considering the random permutations of the array, and best case is big of n when the array is already sorted. And next is hash table operations, where the Rost case is big of n, where all the key hashed to the same slot causing a collision, and average case is big of 1 assuming a good hash function with the uniform distribution. And for binary search, the Rost case is big of log n, that occurs when the element is not found or is the last element to be checked. Average case is big of log n considering a uniform distribution of possible outcomes. And best case is big of 1, that occurs when the element is at the middle of the array. Next, what are the steps that is involved in algorithm analysis? The first step is define the problem and identify the input size. So first we need to clearly state the problem that the algorithm aims to solve. Then we need to determine the parameter that represent the size of the input which will be used in the analysis. The second step is choose the metrics. We need to measure the amount of time an algorithm takes to complete as a function of input size, and we need to measure the amount of memory an algorithm that uses as a function of input size. That we need to compute the time complexity and space complexity of the algorithm. Then the third step is identify the basic operations. That means we need to determine the fundamental operation that most significantly affect the running time or space. And the fourth step is develop a hypothesis. We need to formulate an initial hypothesis about the time and space complexity based on intuition or prior knowledge. The fifth step is analyze the algorithm. That means we need to examine the algorithm step by step to count the number of times the basic operation is executed as a function of the input size. Next is to simplify the expression by using asymptotic analysis. I discuss it later. And next we need to verify the analysis proof by using the proof or empirical testing. That means we need to verify the theoretical analysis by the mathematical proof to ensure the correctness, and empirical testing and benchmarking to compare with the theoretical prediction. Then we need to analyze the best Rost and average cases. I'm already discussed it. And the ninth step is consider the practical constraints. We need to the constant factors and the lower order terms, and environment in architecture. Then the last step is compare with other algorithms by using benchmarking and trade-off. That means benchmarking, we need to compare the analyzed algorithm with other algorithms that solve the same problem to determine which one performs best under various conditions. And using trade-off means we need to consider the trade-off between the time and the space complexity, the ease of implementation, and other factors like the stability and readability. Next is we are going to the topic the time and space complexity of an algorithm. So what is meant by the time complexity? So time complexity means the time complexity of an algorithm that quantifies the amount of time taken by an algorithm to run as a function of the length of the input. Here we need to note that the time to run is a function of length of the input and not the actual execution time of the machine on which the algorithm is running. That means the time complexity, as we discussed about the case of time complexity, the valid algorithm that takes a finite amount of time for execution. So the time required by the algorithm to solve the given problem is called the time complexity. So the time complexity is very useful to measure the useful measure in the analysis of algorithms. So it is the time needed for the completion of an algorithm. So to estimate the time complexity, we need to consider the cost of each fundamental instruction and the number of times the instruction is executed. Here is an example that is given. That is here we are going to add two scalar variables. So the algorithm is given here. So by looking this algorithm, we can say that the addition of two scalar numbers that require one addition operation. So the time complexity of this algorithm is constant. So we can set that the time complexity equal to big of 1. That means in order to calculate the time complexity of an algorithm, it is assumed that a constant time c is taken to execute one operation. So then the total operation for an input length on n are calculated. Next is the space complexity. So the space complexity means the problem solving using computer requires memory to hold a temporary data or final result while the program is in execution. So the amount of memory that required by an algorithm to solve the given problem is called the space complexity of an algorithm. So the space complexity of an algorithm that quantifies the amount of space that taken by an algorithm to run as a function of the length of the input. For an example, the same example that we discussed earlier in the case of time complexity is also given here. So by looking this example, we can say that the addition of two scalar numbers here that require one extra memory location to hold the result. So so we can say that the space complexity of this algorithm is constant. So space complexity can be defined as S of n is equal to big of 1. So next is the asymptotic notation and analysis. So asymptotic analysis can be defined as a big idea that handles the analysis of algorithm. And in asymptotic analysis, here we are going to evaluate the performance of an algorithm in terms of the input size. So we calculate how the time taken by an algorithm increases with the input size as input size increases. And the asymptotic notation is it's a way to describe the running time or the space complexity of an algorithm that is based on the input size. So it is commonly used in the complexity analysis to describe how an algorithm performs as the size of the input grows. So there are three most commonly used notations. They are big of notation, omega notation, and theta notation. So in big of notation, that provide the upper bound on the growth rate of an algorithm's running time or space usage. So it represents the worst case scenario actually. That means the maximum amount of time or space an algorithm may need to solve a problem. For an example, if an algorithm's running time is big of n, then it means that the running time of an algorithm that increases linearly with the input size n or less. Next is omega notation. So the omega notation here to provide the lower bound on the growth rate of an algorithm's running time or space usage, and it represents the best case scenario. That means the minimum amount of time or space an algorithm may need to solve a problem. For an example, if an algorithm's running time is omega of n, then it means that the running time of an algorithm that increases linearly with the input size n or more. Next is theta notation. So the theta notation that provide both the upper and lower bound on the growth rate of an algorithm's running time or space usage. That means it represents the average case scenario, the amount of time or space of an algorithm typically needs to solve a problem. That is the theta notation. So for an example, if an algorithm's running time is theta of n, then it means that the running time of an algorithm that increases linearly with the input size n. And then the analysis of algorithms for constant structures. First we need to start by considering how to count operations in for loops, and first of all aware about the number of iterations of loop and say it x, and then the loop condition is executed x plus 1 times, then each of the statement in the loop body is executed x times, and the loop index update statement is executed x times. So by remembering all these points, we can find the complexity of a loop. Here is an example. So the complexity is determined by the number of iterations in the loop time, the complexity of the body of the loop. So for the first loop, the complexity is big of, we can express this as a big of n, and for second case it is big of n square. For the third example, it is big of log n, and in case of if statement, it can be calculated as the big of max of big of condition 1, big of condition 2, etc., big of branch 1, big of branch 2, etc., big of branch n. So in this case, the highest value is taken, that means the overall complexity is big of n cube. Next is for switch statement, that here we need to take the complexity of the most expensive case including the default case. Here it is big of n square. So this is all about my topic, and thank you.